Okay, welcome friends to this class, which is the continuation of the previous class in which we are discussing about the free endpoint problem. In the free endpoint problem, our final point can terminate to any of the point if there is a variation in the optimal value of the x. So, our general condition appear as the first equation, we can see it here, which is del v by del x d by dt del v by del x dot equals to 0. This is nothing but my Euler equation, and the general boundary condition is given as v dot by del dot x evaluated at the t equal to tf point delta x, then v dot evaluated at tf point minus del v by del x dot again evaluated at the t equal to tf point x dot tf delta tf equal to 0. So, this is the general condition. For this general condition, we have the different cases, like we can have the fixed endpoint problem. In the fixed endpoint problem, delta xf and delta tf both are 0. So, this means the second equation will not appear in that case, and we have to solve the problem using the EL equation, which will lead to a differential equation with given boundary condition. So, in this case my boundary condition is the initial condition as well as the my terminal condition. The second case we have considered that in which TF was fixed. So, delta TF was 0 and the XTF was free. So, in that case, if this delta XF variation is arbitrary, my del V by del X dot will be 0. Third case we have taken that in which my TF is free, but XTF is fixed. If XTF is fixed, this means my delta XF will be 0. If delta XF is 0, delta TF is arbitrary, the coefficient of the delta TF that will also be 0. So, these three cases we already have been discussed in the previous classes. So, today we will take the case 4 in which my TF and the XTF are free. If TF and the XTF are free, so we have my general condition which is given by these two equations. So, my first equation will appear in the similar manner, which will be my Euler equation, and terminal condition will be the given by second equation. So, we can say my fourth case is TF and x of TF is free. This will further lead to the two sub cases. The first one is if TF and XTF are unrelated. This means my TF and the XTF both are the independent variable. If both are independent, so naturally in this case whatever be the coefficient of the delta XF, that will be 0, and what is the coefficient of the delta TF, that will be 0, because both delta XF and the delta TF, these will be arbitrary. So, in case of the my first sub case in which TF and the XTF are unrelated, so this means I can write delta V dot by delta X dot evaluated at t equal to TF point, that will be 0, and V dot evaluated at T equal to TF point minus del V by del X dot, again evaluated at T equal to TF point X dot TF, that will be equal to 0. So, as we are seeing in this case, my first term del V by del X dot, this is nothing but the coefficient of the delta XF, and the second term is the coefficient of the delta TF. Both delta XF and delta TF are arbitrary, so their coefficient will be 0. So, my first case in which the TF and the XTF are unrelated, my boundary condition will be governed by the del V by del X dot equal to 0, and the second equation is del V by V evaluated at T equal to TF point minus del V by del X dot TF, that must be equal to 0. So, in this case my V dot is nothing but V evaluated at X star dot and T points. So, this is my first case. In the second case, if these two will be related, so the second case we are saying, if TF and the XTF are related, means there may be the case that any one of may be the dependent variable of the other. So, one if I am treating as a independent, the other may be the dependent on the first variable. Let us take an example in this case. Let us say this is my X star, this is my general boundary condition, and let us say this is my another curve which is given as theta t. So, this is T0, this is nothing but my TF. So, this is the same as we have discussed in the previous class, TF plus delta TF, this is my X star plus delta X, the variation into this, and this is my X of TF. So, as we are saying TF and the XTF are related to each other, let us say my optimal trajectory terminate to a curve given by theta t. So, in this case my X of TF nothing but will be equal to theta of TF. So, my XTF will be equal to theta TF. This means at the end point my trajectory is terminating at this given point. So, if this is terminating, then how we can relate this? So, delta XF I can approximate as d theta at TF point by dt into delta TF. So, by this I can approximate, or simply I can write this as theta dot at TF point delta TF. So, XF can be approximated in terms of the theta f if there is a relation between x and theta at any given condition. So, here we have the condition which we have considered as my trajectory is terminating to the theta t curve. So, XTF is equal to theta TF. So, again if I will consider my general condition, like given in this case. So, this delta xf I am trying to relate with the delta tf. So, if I will place the value of the delta xf calculated on the board into this expression, so I will get a simple equation in delta tf, which will be. So, now boundary condition can be written as so I am just simply placing the value of the delta xf in my last equation. If I will place this value, this is my equation will become del v dot by del x dot, this value evaluated at t equal to tf point, theta dot of tf plus v evaluated at t equal to tf point minus del v dot by del x dot at t equal to tf point, x dot of tf and the whole multiplied with delta tf, and this must be equal to 0. So, by substituting the value of delta xf in my last equation, I get this value. So, del v by del x, so I can combine these term and can write my boundary condition treating delta tf to be the arbitrary. So, the coefficient of the delta tf will be 0. So, my final boundary condition will be del v by del x dot, which I am taking out from this expression. Sorry, this is at t equal to tf point, this whole multiplied with the theta dot of tf minus x dot of tf plus v dot at t equal to tf point equals to 0. So, this will be my final boundary condition. So, this we can say that if tf and the xtf are free and related to each other by the curve theta t, and my trajectory is terminating to the curve theta t. So, my end point xtf will be equal to theta of tf, then my final boundary condition will be del v by del x dot theta dot minus x dot tf plus del v equals to 0. So, this is my fourth case. Let us take an example to understand this more clearly. So, for this second sub case we will take an problem. The statement of the problem is find an extremal curve for the functional Jx equal to to the power half dt. The boundary conditions are t0 equal to 0 and xt0 equal to 0 and tf and xtf are free, but xtf is required to lie on the line theta t equal to minus 5t plus 50. So, my problem is we have to find an extremal curve for the given functional with the boundary condition given as t0 equal to 0, xt0 equal to 0 and tf and the xtf are free, but here we are putting a condition xtf is required to lie on the line theta t equal to minus 5t plus 15. So, now if you will see what actually my problem is. So, I have to start with the origin t equal to 0, xt 0. This is my theta t line which is minus 5t plus 15. So, t equal to 0. So, this value is 15. This is if theta t is 0. So, this will be nothing but 3. So, this is my theta t line. So, I have to find what will be my optimal curve for. So, this distance should be the minimal distance. So, this problem we have to solve. So, as you can see, what is my functional? This is nothing but, if you can recall our previous problem, we are trying to find out the minimal curve which is joining the 2 points. So, from there we have taken this functional. So, this we are directly treating at this point. To solve this problem, we will take first solve the EL equation and then we will apply our final condition to get out the to get the value of my constants. So, the solution of this problem, so naturally first we have to write del v by del x minus d by dt. So, EL equation we will write first del v by del x dot, that must be equal to 0. In this case, my v is 1 plus x dot square t to the power half. So, del v by del x is 0, we already have been solved this problem. D by dt x dot t by 1 plus x dot square t to the power half, that is equal to 0. So, this nothing but gives us x double dot t equals to 0, and the solution of this, which is nothing but my optimal, x star t is C1 t plus C2. and using the boundary condition my objective is to find out the constant C1 and C2. So, my first condition is directly is x0 equal to 0. So, if t is 0, so C1 will be 0, nothing but C2. This implies my C2 value coming out to be 0. So, C2 is 0, that we can find out from my initial conditions, which is given x0 equal to 0, and C1 can be determined utilizing the endpoint condition which we have derived just now, del v by del x dot at t equal to tf point theta dot tf minus x dot tf plus v at the point t equal to tf and equating it to 0. So, let us see what we will get in this. My another boundary condition so I have del v dot by del x dot. So, let us write here del v by del x dot at t equal to tf point theta dot tf minus x dot tf plus v dot t equal to tf point, that must be equal to. So, this is my another boundary condition. So, with the given v I will find out del v by del x, which is nothing but given by this equation at tf point. So, I can write this is as x dot of tf 1 plus x square dot of tf square root of this theta dot of tf. What was my theta? My theta was minus 5t plus 15. So, theta dot tf is nothing but minus 5. So, this is minus 5 minus x dot of tf, and what is v at tf point? 1 plus x dot square of tf, and that must be equal to 0. So, we are given with my last condition. So, if I will solve this, so I am getting this minus 5 x dot of tf plus 1, that must be equal to 0. What was my xt? Xt is C1t plus C2. So, x dot of Tf is nothing but my C1. So, x dot of Tf if I will find, that will be nothing but my C1. So, this is minus 5 C1 plus 1 equal to 0. So, C1 nothing but is my 1 by 5. So, this means my optimal trajectory x star t, which is C1 t, nothing but 1 by 5 t, C2 is 0. So, this will be my optimal value of the x. Similarly, we can extend this. Now find TF, and TF we can find because we know my terminal condition XTF equal to theta TF XTF is 1 by 5 TF, because X star T is this 1 by 5 TF, and theta is minus 5 TF plus 15, and this give you TF equal to 75 by 26, which is equal to, we can write as 2.88. So, using this, so this will be my final solution. So, my final solution I can find out in the following manner. So, in a free endpoint problem, we will try to find out the different cases. This means normally we are given with the initial point and where my terminal point is will be. So, the 4 cases we have discussed. The first one is the fixed endpoint problem. Second, my XTF is free, TF is fixed. The third, XTF is fixed, TF is free, and when both are the free. So, these 4 cases along with the example we have seen here. So, this is the free endpoint problem when we are simply trying to extremize a given functional without any condition. So, in this case we have not considered any condition. In our next part we will consider the variational problem with the given condition. So, this lecture I stop it here, and in the next lecture we will start our discussion on the extremization of the functional with condition. We will start with the function extremization and then we will lead to the functional extremization. Thank you very much.